Welcome to your Engineering Design Challenge. Today you'll use science and creative thinking to craft solutions for real-world dilemmas. We're going to turn these into these. Wow! As we work, we should keep in mind that surfaces can have different kinds of curvature: positive, zero, and negative. The curvature of a surface is determined by the sum of the internal angles measured at a vertex, and the vertex is the point where the corners of our tile pieces come together. These definitions will come in handy during our design challenge. Let's start with the dome. Domes are useful because they distribute weight and pressure around the entire structure. They use geometry to increase the strength without adding additional material. Check out this egg carton cup, which is really strong without using all that much paper. We can also construct domes from tiles or beads. They're super strong thanks to geometry. Now it's your turn. Can you make a dome from these pieces? Here's a hint. Domes have positive curvature. Pause the video while you give it a try. All right, here comes the answer. Does your answer match mine? I connected the squares in a plus sign and used the triangles to form 4 vertices, each with angle sums less than 360 degrees. So the overall dome shape has positive curvature. Crafters have used positive curvature for generations. That's how you can put curves into the bottom of a basket or the heel of a sock. All right, next up, we have a saddle. It curves up in one direction and down in the perpendicular direction. Shapes like this allow you to squeeze more surface area into a smaller perimeter. By creating ruffles into the third dimension, you can more efficiently use the space. So when it comes to potato chips, you get more chip per chip than if they were just flat circles in the tin. And wavy edges like this can be flexible. Some creatures, like this nudibranch, use their frills to swim. And when you make saddle surfaces out of tiles or beads, their edges can also be flexible and wave around. It's your turn. Can you make a saddle from these pieces? Here's another hint. Saddles have negative curvature. So pause the video and give it a try. Okay, here we go. Answer in 3, 2, 1. How'd you do? I put the heptagon in the center and connected the hexagons to each of the 7 edges. At every vertex of the heptagon, the interior angles sum to more than 360 degrees, so the overall saddle shape has negative curvature. Dressmakers use negative curvatures to create flouncy sleeves or skirts, like the ruffles all over this flamenco dancer's skirt, which is the type of dancer the nudibranch is named after. Now, what about shapes that are totally enclosed so that you can store stuff inside? For example, sports balls. They hold air so that we can play some of our favorite games, and pouches let us carry stuff around. All of these sports balls are made of flat shapes, or tiles really, stitched together to create enclosed 3D shapes with positive curvature. Can you make a totally enclosed shape using these tiles? Here's your final hint. Enclosed shapes have overall positive curvature, and every single edge should be connected in your final structure. Pause the video one last time to give it a try. All right, final answer coming in 3, 2, 1. How'd you do? It was a little tricky for me, but I found a way to connect all the pentagons to each other so that they formed a completely enclosed shape. This is called a dodecahedron. Because every vertex had 3 pentagons, their angles summed to less than 360 degrees, and the entire structure has positive curvature. Geometry and tiling are super helpful for turning flat materials like leather or cardboard or metal beams into enclosed structures like bags, boxes, or even buildings. And that's really what craft is all about. Turning small pieces into larger, more functional structures. Oh, hold on. Professor Trevor wants to congratulate you on completing your engineering design challenge. Here's his special message.
Congratulations on completing the engineering challenge, everyone. With this work, I hope you see that the rules of crafting connect to some of the design rules used in engineering. In many ways, the artistic decisions you use to build certain forms or functions are actually mathematical operations used to build materials. With these lessons, you should have gotten to the heart of craft and matter, where things like cutting or folding paper, weaving or knitting threads, or linking beads together can build materials, and where complex things can be described by simpler theories. Miigwech!